Okay, let's start with the usual slides regarding quantum technologies. Well, it's all based the quantum information theory, and we have three pillars: quantum computation, communication, and sensing. But these also have some subsections like simulations in computation segment, and communications have also cryptography, and sensing also have metrology together. For an integrated approach, you need something integrable. You need to build from you need to sample from the building blocks. What is the state of the art? We have trapped ions, which was the hardest to integrate, but now it's in the chip. Already can be trapped in a very small chip, several of them. And there are lots of big companies over there. And also, you know, the superconducting qubits, which is the major development. It was the major workhouse, and it was attracting the major investment till this year. And this year, the nanophotonics is leading the investment. If we already knew the news from the Australian government. Anyway, let's check out the map of the quantum computing. By the way, this is a very good book for a regular audience, not specialized in physics or etc., or specialized in different kind of branch of the physics. This Oliver Ezrati is kind of science communicator. This is a very extended book, and updated last year around this time. It's like several hundred pages, all the companies, all the relevant technology, all the basic building blocks, everything is included here. So it's a good introduction to these terms, what they mean, what already explained here, what is the connection between them, okay? So for a quantum computing, what do you need? I will get in more detail, but let's say now we are just considering the gate-based quantum computing. You need the qubits, discrete variable states. You need something discrete, quantizable. Yeah, you mean this discrete states. Also, what do you need? You need to somehow program these qubits and make some undisturbing or unitary operations on this gate, qubits, all right? So you don't want to measure them unless you are ready to measure them. So you just need to, for example, do some, as a classical sense, you need to do some rotations on some coordinate system. But it's not easy. I will talk about the noise part, which is the most important part now for anything to be scalable, or what kind of scalability we need. And this is a regular slide. I will not hang in here too much. What is the quantum computer? What is the standard computer? But in real world, we use deterministic computers, right? Which means we want to get deterministic answers. For example, if I add some number to some number, I want to result, just some mathematical basic calculation, and result will be never different, okay? Because it's deterministic. It doesn't depend on me. But in real world, especially when you have too much information, like not a few centuries ago, now we have the possibilities. And you need something, you need some technology to calculate these possibilities. Of course, we have analog computers from like 2000 years. All right, if you check the literature, there are already good example for analog computers. It doesn't have to be electronical. But we need something to calculate the possibilities with some kind of new technology effectively. And sometimes we don't need to calculate every possibility of outcome from a system, just one or two outcomes. So this is the quantum computers can do better in principle. And there are also good algorithms, etc. I won't get into detail, and it's not my specialty, like Fourier transform, etc., or factorizing the prime numbers. But you already heard some qubit states, like two-level systems, but now it's the leading technology already has behind the two-level systems, the three-level system, four-level system. And as you can see, the advantage it's order n. It's not order n, exponential n, but you see the base number is improving now. It's not a big improvement, you may see like that, but in the end, I will mention later, for logical qubit technology improvement, we need this kind of approaches. And this different states also enable new error correction algorithms. Okay, how do we gates operate for simple system? So you have an input system, you have a headline algorithm, I don't know what, but you need to operate some gates, like logical operations. Then there is a physical implementation on the system, as you can see. It is just interference between the states. It might be Hadamard, or it might be CNOT, or etc., but it depends on the interference. For photons, it requires indistinguishability. Otherwise, they will not. Or, for example, you might have some state here. For example, one single photon comes here, or single qubit comes here from there. They might interfere since they indistinguishability, but if they lose their coherence or this property, they won't interfere here. So if the values in the visibility of indistinguishability is higher, then you can operate many times on this qubits. And this is the error, and is the purity of state, you can call it. If it's pure, for example, for recently they announced they improved the purity of the qubits from 99.98 to 99. It's like 1% improvement, but it's already reduced few hundreds or not thousands of the qubits for a real physical system requirement. Okay, you know the classical logic gates. People like these slides actually from perspective of software engineer, computer engineer, or low-level electronic engineer. You want to think that way. So you are just creating some correspondent gates like that. But as a warning, never forget that this left side is deterministic, right side is probabilistic computer. So they're from different realms. I won't get to all the details because it's already different. But if you look at the quantum gates available for photonic quantum computers, we see for example, all the technology. We see the trapped ions, cold atoms, superconducting silicon spin centers, NV center, or mostly debatable Majorana fermions. No one saw them yet, or photons. You see that there are single qubit gates, 2 qubit gates, and most. Can you guys hear me from the Zoom? Okay, now it's switched back. Okay. I think I just misstep on a cable, sorry. As you can see, there are single qubit gates which widely available any technology easily, which means you just interact them in some way. It might be local qubit, it might be flying qubit like photons. They can you just manipulate them one by one. For example, sending a photon to a beam splitter or half-wave plate. That's it. But if you want to interact two of them simultaneously on a gate or interferometer, etc., think about it, then the photons fail since they don't want to interact each other. Okay, for now the term flying qubits comes here. All the other technologies are stationary qubits, which means they are localized on the material system or the whatever technology is. They stay safe. So interact them like it's like it's like a game, but it's a stationary. They interact. If it's done, then you can reinitialize them, and the neighbors you can reinitialize them, and the information is like processed like standard usual computer from today. But the photon qubits, if you emit a photon, it needs to travel. You can trap it time that rapid or put in a memory. There is another commercial photonic quantum computing using quantum memories or trying to use quantum memories for this approach, but it's limited. It will decay. It will lose since it's a single photon. If you lose it, that's all. So the term comes from the flying qubits. You need to make gate operation measurements on the fly when it happens. So you need to be fast. That's another requirement for this system. And the photons, there are several quantum light sources or approaches for information. Well, such one is unique photons, which calls it's a single photon state, continuous variable. I will not go into coherent Ising machines. It's not the topic of the day. But from these continuous variables and the unique photons, means single photons, you can generate cluster state. I think it's already mentioned yesterday, or I will mention today. Non-Gaussian state, and you can use this information to already calculate some boson sampling. This is some kind of special algorithm-based computer. It does that, nothing more yet. But if you want to do more, if you want to build some universal photonic quantum computer, then you need two more approaches, which measurement based or normal universal gate operation. Okay, what happens in a quantum computing system? If you look at it, you initialize a state. It might be ready, it might not be ready. For example, you can emit a single photon, but you might need to change its phase a little bit to interact with other photons to get a Hongo-Mandel interference. Otherwise, it won't be ready. So this stage is called preparation. It's on a chip, either on an optical system, it doesn't matter. Or you want to create some time multiplex states like the Professor Emre mentioned yesterday afternoon. There is some initialization and preparation state. Then for gate-based system, then you have some gates, unitary transformation on the states, all right? You don't measure them, you just project them in arbitrary direction for its convenience for your algorithm. Then you do some data manipulation and you do some measurement. And if you like this velocipede, you can easily see it. For example, you create a zero state. Either you can call it polarization state or spin state, etc. Depends on your computer. Then you operate a Hadamard gate to create a superposition of this both up and down states. Then you can manipulate the rotations. Then you measure it for different bases. Then you get the results. It's actually easy in principle. So what are the key parameters for or requirements for a quantum computer? This is for gate-based quantum computing technology, but most of them are true for both technology. So you need well-characterized qubits, distinct states, but they has to be scalable. So tabletop systems, they have limited ability for integration. So you need something initializable, which means I want them to operate whenever I want. Okay, and you need long coherence times. What does mean? If you want to lots of sequential gate operation on qubits, you need a coherence time longer than this, which is called path length or total path length. All right. Then you need some set of sets. Yeah, I mean universal gate quantum gate set, which is like for algebra we use addition, multiplication. You can divide, etc., and you can create whatever result you have. And this is the basic operations, right? And you need similar some complex set of operations to do that. Then you need to be able to measure it, which is the important part. For example, with some kind of CNOT, you can create some entanglement, but if you cannot measure it with some realistic setup, then it doesn't work for you. Okay, for photonic quantum computing, or if you have several quantum computers, or if you don't want your quantum information, you don't want to transfer your quantum information, the classical information on the quantum computer. For example, you have some local quantum computer, then you have another quantum computer separated by a distance, I don't know how much, but you want them to correlate their quantum results, do some another calculation or some another interference. Then you need to convert it to telecom wavelengths. It's about 1.5 micrometer as a wavelength. Why? Because since it's a very weak signal, if for example it's an RF signal like superconductings, it will be a few gigahertz. All right. Then if you try to get this gigahertz signal from your cryostat, you will just get noise, nothing else. But if you try to convert them to optic frequencies, this another active research area, then you can convert to normal communication frequencies, which we have very, I don't know how many very over there, but they sell it very low attenuated optical fibers, which they don't absorb or lose the photons you insert them easily. So we need this approach, and yeah, and the number of qubits. This is the physical qubits. I mean, I will get into detail, but for a universal qubit with error correction system like the superconducting system, for example, if you need 1 million logical qubit, you will need 10 to the 14 physical qubits. Unfortunately, this is the case because the quantum error correction requires a family of the physical qubits in the system. So you, for example, if your technology is limited some wafer size like 10-inch or 2-inch, I don't know, some millimeter diameter, then no need to scale, or no need, you shouldn't study on this system or material platform. Then you need the qubit connectivity. This is another thing. Well, if you want to increase your, for example, you have very fast electronics and you want to change the phase, etc., or gate operation in a system, then your system will be needs to have this speed also, and you might need some qubit parallel operation, fidelities, execution type, operation temperature. It depends on your system. Superconductors require very low temperatures, for example, and total energy consumption. It's like AI. It's good, but it's heating our planet, so it's bad for now. It will stay that way. You know what AI does. We will try to reduce our carbon footprint, but AI will make it worse. And this is the same for quantum computer. It's now, you may say it's now, okay, it's funny, there are few of them, but what happens if the number increases like AI firms? Then we need to consider this approach too. And systems, total system rackability. You might need to move it around and put in some closed enclosure. Okay, now if you focus on the photons, if we compare them, for example, how qubit size, if on the cold atoms, we requires like 1 micrometer space for its trapping area, basically, or trapped ions. So for superconductors, we have some 100 micrometer square area for this circuit. And for silicon, it gets a little bit lower. For MV center, it's lower, but photons, well, your photons on the fly, but how do you produce, how do you, etc. You need some non-photonic approach, and luckily we have several available platforms already there. CMOS-based silicon nitride, and not CMOS-based indium phosphide, etc. already here. And we checked Dandy for gate-based operation. 2 cubic gate fidelities. This is a little bit old. For example, like I said, the gate fidelities of here updated already to 5% better, like yesterday, from TÜBİTAK. And superconductance is lagging behind, but I think they also improved too. And the best qubit gate fidelities, photons is bad, very bad. And then there is the readout fidelity, which measurement of the system, and you see photons again bad. And you check the gate operation time, and well, it's comparable for all systems. Some of very bad, but it depends on their electronic control technology mostly. You can adjust it in future. It's not that bad. Then the temperatures, then etc. But you get the message. The gate-based computing is not for photons in general. Well, it's general concept now. Since this is the general concept, not the commercial products or commercial companies not following this path because of this. Gate-based is not for photons. So photons qubit technology, from the gate-based perspective, you can generate discrete variable or qubit states from polarization, frequency, amplitude, phase, mode, path trail, photon number. You have like 10 of degrees of the freedom to obtain it, and you can get the stable qubit with absence of the coherence, which is affect the other system. For example, if you have a superconducting system, you already lower the temperature to 10 millikelvin, so phonons doesn't do much around, but the material properties can also create some discrepancies between the qubits. So this is a very problematic way, and you need to shield it carefully to any RF or electromagnetic wave shouldn't get in their system. There's another problem. But with the photons, well, they don't like to interact even with each other, even with the material. So their absorption cross-section is very low for any photon in any material. So you can also operate qubits in room temperature. You can use emerging nanophotonic manufacturing techniques. This is like the transistor is discovered 50s, 60s. Then the silicon CMOS technology reach a trend to get a fast improving trend like 60s, 70s. Then it's boom. We are using very super computers in our pockets now, and this is the area for nanophotonics now. Probably you will hear like 5 years, 10 years, there will be nanophotonic processing chips, not for quantum computing, for regular computing. So it's a good time to start that, and it's easy to interact, and there are also some approaches. But the problem comes from the regular detectors we use every day, like in the camera, silicon, in gallium arsenide, I already talked about. They are not good for computation approaches because you don't want any loss at all. You are working on single photon level. So loss means loss of information. Then what you do, you multiply the system. You get you are simulating a qubit, which means logical qubit, with several other qubits, real physical qubits. All right, and already, I mean, from my perspective, it's already only quantum advantage shown today is the Boson sampling, because it's so hard for a deterministic computer. But then again, some clever guys come up with a clever algorithm can work on a classical computer, but we don't know yet. So what is the I want to call this like algorithmic approach for hardware. I mean, you want to solve something, you have a problem, you have some nice algorithm for it, can be implanted in universal gate computing or etc. You don't know the platform, but then you need some hardware algorithm to implement it. How do you propose to solve this problem? What we have, quantum simulators, they are just analog computers. Okay, so then we can use the gate-based computing, which is called today linear optical quantum computing. I will get into detail. And then you can use some specific purpose, multi-purpose devices. For example, if you already know or don't know, I mean, we don't build universal CPUs in Turkey or produce them, fabricate them. But in the TÜBİTAK, for example, there are some task-specific CPU-like structures are built in here in Aselsan, in other companies. This is we call them specific purpose systems. So you can already build them with photonic computers. And there's another approach, measurement-based quantum computing. And what you do, I will get in more detail a little bit today. But what you do, instead of using gates to manipulate the qubit, you do measurements for gate manipulation or in sense of gate manipulation. All right. So what we the rival technologies, we see them together with photons, gate-based quantum computing. It's possible, but not it's not a preferable thing. And analog quantum simulation, like I said, in continuous variable mode, is already okay. And you can use quantum memory, which is good, and other quantum technologies, quantum sensing, quantum telecoms, etc., already possible. And if you check the chart, usually what you say, most of them work on gate-based quantum computing. So this is why you are the information getting pumped in the literature or the media due to this, because they work on gate-based computing. But this is not the singular approach. Okay, so what is the challenges, solutions, or what we can propose for photons? Well, sorry. I will not get into the details of all the challenges in this topic, but for photons, well, the photon statistic, for example, you don't always get the perfect single photon states from the photons. You need improvement, but for example, from a superconducting circuit, it's a macroscopic structure with a macroscopic lithography. So it's a lot more easy to obtain from these systems. Okay, then we will talk about it later, but for other approaches other than the gate-based photonic computer, you need to create entanglement between other entangled states, which is called cluster state. Okay, so it's a little bit hard for photons because they don't like to interact each other. So what you require, for example, bright and deterministic photon source, which means if you remember the first day talk, you want a photon source when I want to emit, you want to emit a photon when I want. It should be deterministic. It shouldn't happen like when it wants. Okay, because I want to control the measurement or gate, but we can get a clever ways to overcome this obstacle. The determinate and also you need deterministic source of cluster states again from the deterministic problems, and also you have the integrated nanophotonic technology already available for like each other of you. If you have a clever nanophotonic device already you simulated, for example, you want to use this solution, you can just order it for 5,000 euros in Europe already. It's a production level now. And yeah. So what hardware components of this system? Well, classical part mostly same, which is like data access, like signal manipulation, RF sources, etc. Almost all of them same. Then you need some classical computer to interpret this measurement. Like then this is the same approach. For photons, then it's a little bit different from the, for example, superconductors, but like ions, neutral atoms, etc., they also use lasers or similar systems to excite these ions, but they don't use this emission from the systems. Then you need photon source and detectors. You might want to use cool down your system, etc., but some of them is in common. So if we now look at the noise and classification of quantum computers, well, what from experimental view, what is the source of noise? Well, unfortunately, it's very pure material. For example, you may dream of some room temperature superconducting structure, but unfortunately, then you need a perfect material, and you also need to get away from this thermal fluctuations. All right. And another thing is electromagnetic noise you are introducing to this system, because you are controlling a system. You are sending some signal over there, right? If it's a little bit time dependence over there, you will create some magnetic field. So, and your system, since it acts like a qubit for superconducting or real qubit, or if it has a spin property, then bye bye. You lost your coherence of your spins. And you may have also a crosstalk between these qubits if they are close to packet to each other. All right. And what do you have now? Again, of course, the cosmic background radiation. So you need shields, etc. Even gravity at this level affects everything. And lastly, but not leastly, the quantum vacuum fluctuations. For example, if you are working with the continuous variable system, you are already working in this region, so it's also affect your systems. All of them introduce some error. It might depend your system, your material, or the environment. But what is good? What do you need? We need quantum gate error rate 10 to the minus 15. This is a very, very low number. How do you get this number? This is what we impose on the classical deterministic computers now. Why? This is because why they have so many transistors with some imperfections in them. All right. So you simulate one qubit, physical qubit, with several or maybe hundreds of thousands of the physical qubits to get a behavior of a real logical qubit or real qubit. So, but so we already see IBM, Google, or the other technologies in the below the 99 qubit fidelity rates. I mean gate fidelity rates. But if you increase the number of the gates on your system, this number gets evolved, and you need to improve. You need to add additional qubits to simulate this behavior of the system. How about the photonic quantum computers? Well, the thing is NICQ is noise intolerant, noise tolerant or noisy environment qubits, yeah, which already see 98% qubit error rate or measurement rate. Then if it's a little bit higher, you can large scale it, LSQ region, or you can, if it improved a little bit, you can go to fault tolerant quantum computing region, which is the aim of the photonic computers. But for very large scale quantum computing, the aim of the superconducting or ion trap technology in these days. So you see the requirement, physical qubit requirement for large scale, 20 million, for example, logical. For 20 million physical qubits, you get only 4,000 logical qubits. And there is a very high gap over there. Okay. So now I will mention about what technology is used for commercially or commercial. How can I say it? But commercial level or something already shown by a prestigious research group. Like say, I'm not going to get into detail every circuit of every qubit or gate operation in the literature, but what is already shown. For example, if a system shown already boson sampling advantage, we will mention about it. Okay. Now, if you look at the history of the implantation of the photonic quantum computers, on-chip quantum interference and CNOT gates implanted after 7 years after its first mention in the literature by KLM. I will get into detail. And around to like 15 years ago, its first programmable QPU for photonic computers implanted. It's a little bit basic model, but you see the, for example, silicon SNSPD over there. Then you see the silicon source and the circuit. Now they're pushing it, and we now the 8 photon processing here. It's a little bit of 6-year-old chart, but what we have now, we have 20 by 20 qubit operational devices now, for single qubits, discrete level systems. So now, if you look at the problem, you have a system consistent of qubits doesn't like the interact each other. So problem is and creation correlations or interact or in making force them to interact with each other. Well, this is the basic controlled CNOT quantum gate. You can a swap gate and C-phase gate, which is commonly used for other technologies, can be derived from this CNOT gate with some additional unitary operations. All right. So it's basically you want to it's like let me give this you want to create like something familiar to SPDC process. You want to send 2 signals in. You want to get 2 signals out, but they has to be correlated, quantumly correlated in some degrees of freedom. For example, like photon entangled, polarization entangled, etc. All right. But you can already use like the nonlinear interactions I already mentioned. But if you remember the probability of this nonlinear interaction event is our best manufacturer abilities is 10 to the minus 6, 1 over million. So you need 1 million 1 million gates to get 1% in theory. Actually, you need to get a larger system to get this 100% probability, successful probability from this media. But this is not the only approach. So depending on this, the literature chooses 2 ways. One is what we call is now, it was firstly mentioned, teleportation based quantum computing, which is you teleport the states. You create a non-linearity by using linearity. Okay, I will mention that later. But then we have also another approach, measurement-based quantum computing. So we see them side by side. In the left side, we have the gate-based operations. As you see, gates are the operators of your system. So you use unitary transformation to, without measuring them, change the phase, etc. But for the measurement-based quantum operation, you see there are some creating your connections over there. Let me see from here, for example, or here. These are creating by measuring the system. From a gate-based quantum computing perspective, this is the first approach. Destructive gate-based photonic quantum computing. Well, you create some state, you create some QPU with the system, which is a famous paper you can already check in 2001 with the authors already there. It's basically use of some supporting photons to your system. Like it's since already available. If you remember the heralding photons from the SPDC, you get the photon pairs. All right. If you send this to the system, for example, over here, you have a control and you have a C and T input. I will not get into too much detail of this. and you want, in the end, you want to see is affected by T or otherwise, all right? They want to be interact each other, but you since you don't have the ability to interact directly, you implant a beam splitter, phase shifter, basically makes enter interferometer-like structure. What you do, you send heralding single photons from 4 of these ports. Then you want them to interact, but you need to measure all of them in the end. So if you measure them, and there is no qubit available to process after this gate. So what means is this: you making some gate implantation, but you are destroying the qubit. So this was not. This is still working. I mean, this paper is like 10 years ago, but there are some improvements on this. But this is a data approach for gate-based quantum computer. What you can do, you can also. This is a little bit. I'm sorry. This is a little bit clear here. For example, for CNOT gate, like this in the here, you have C in, T in, and C out, T out for a CNOT gate. Okay, from the A. Then you have this physical implantation here. You have 2 beam splitters. Okay, but you are feeding entangled state to this system. All right. And you are now measuring only the heralding states, or the one of the outputs of these beam splitters, not all of them, 4 of them, but measuring them the states with 4 detectors to get. This is a polarization qubit, so you don't destroy the states. And I forgot to mention, this is a 1 over, in the original approach, you can be successful with 1/16 probability with this gate. Every time you try, you have a success of probability 1/16. With this system, it's kind of same, but it can be easily manipulated. But then again, you are trying to interact 2 photons with a very expensive cost. You are using too many states, too many entangled photons, too many gates, too many. Again, this is not different from the physical quantum error correction with the superconducting systems, with the logical qubit approach. But now what are you doing? You are using logical gates with additional physical gates to manipulate the systems. So this is the linear quantum optic computer. And there is another new approach. I am not the expert on this topic, at least the physical, theoretical implantation, but since 2-bit gate is a unitary transformation, you can also make a linear combination of this. It can be shown from this paper. You can create a linear combination of linear single qubit operations to show that. So this is another approach. So, for example, this is a simple. Most of it, I can scale it. Most of it, this you see the complex stability here. This is just a CNOT gate. We are trying to do something, a very 2 qubit interaction with a very complex way. Again, maybe people start to think about maybe we are forcing the photons to compute something in a wrong way. So what was the next one is the measurement-based photonic computing. So with the gate-based photonic computing, you have this advantage. You can, even with the flying photons, flying qubits, it can go either way. It doesn't need to be one direction, but the measurement-based, you always measure something to get gate operations. So it's one-way computing, also called one-way computing, all right? So what we use in this measurement-based computing, only single qubit gates, nothing else. And the measurements are the computation or the gate operations. But then you need, for effectively compute a larger system or behavior of the larger system, you need entangled cluster states, not the single qubit states. So you need entangled state with the higher degrees of freedom, higher degrees of entanglement. I will get into that later. But then again, what can you do with the, like I say, specific purpose system, task-oriented quantum photonic computers? For example, you already saw boson sampling, simulate localization with the boson same system with the boson sampling. You can simulate the quantum transport, simulate the molecular energy changes of some system vibrational changes also. And you can use some algorithm. This is new one, Hamiltonian learning, and this is the most used, the Galton board simulation. So, like I already mentioned in like 2 days ago, if you have some problem with every step, if it has multiple outcomes, it's like putting beam splitters after each after. All right, you just building up those beam splitters like this, and if you check the Galton board, it's already like beam splitters like structures. For example, if particles come from there, it's a classical description of the system. It's either goes right or left, then goes to bottom, right or left, right or left, right or left. It's just basic beam splitter structure, which is done, but you need to adjust the phases. It has to be, if two photons come together, they want them to interact, then it's Mach-Center interferometers, lots of them, okay? So what is the literature studying now? As you can see from the right side, you can see the system. I like this analogy. For example, we have CPUs, right? But we have also GPUs now, and we see GPUs are the GPUs have way more performance, some specific tasks compared to the CPU. So you can think it's a little like GPU structure. And this is the newest one, quantum machine learning with some continuous variable system. This is a little bit complicated now, but I just want to show the system for later phases. There is some method, quantum kernel method for quantum machine learning. You can already use this a very basic optical setup like this side on your table to study this system. So this is also task-based. For example, machine learning, you have some machine learning problem, quantum machine learning problem. You don't need the universal gate computing, what I'm trying to say. And if you look at the companies now, I think we can take do we have 4 minutes or? Yeah, okay. That you already hit, there are a little bit more companies, but PsiQuantum is got the fund like $1 billion as an investment from government. There are a lot of debate why they got it, why do they have it, we don't know. But what I will talk about this discrete variable quantum computing. You can see it like again measurement-based approach. Quandela also discrete variable. If you use single photon space, Xanadu, well, it used continuous variables for quantum computing, and Qubits also discrete variable quantum computing, and Orca is another UK-based company. It used memories to store photons before each operation, but I won't get into this. It's far sophisticated concept for this school. But if you remember this slide on the left side, we have discrete variable degrees of freedom to create single photon states, and in the right side we see the continuous variable Q modes. It's just a reminder. Then, by the way, to compare these CV state, Qubit state, this is from the Strawberry Fields AI website. It is from Xanadu's, like IBM's interface or software algorithm interface website. There are lots of useful information, even for an engineer here. So I want, if you want to visit, it's great. So you have Q modes. What is like operators? You have qubits, What is operators? Parallel operators is basically rotation operators in the right side, left side. You have some anti-commuting operations, and the common states are the for CV. What we usually have is Gaussian states. It's either coherent states or squeeze state. But for quantum computing, it's coherent states is not preferable. It's for quantum quantum K distribution. Gaussian states is mostly used. This coherent states mostly used, but squeeze states is a good for quantum computing. And you see the available common gates. So for continuous variable, you might already see the phase diagrams. So you originally start in the center of the phase. So if you want to get a different point of this phase diagram, this XY, X1, X2 diagram, basically, or Wigner space representation, you need to use some displacement operator. So this is from the theoretical perspective view. And you also create some squeezing on this, for example, coherent state to make it not round, but squeeze state in the either momentum or positional direction, for example. And the measurement methods for single photon states, for discrete variable, you need single photon detectors. Like I said, you need to cool them down. They are extremely expensive, but the continuous variable system, you just regular photodiodes. But you check the frequency response of these photodiodes. Okay, now we look at the companies now one by one just after the break, I guess. Okay.